So we'll do start. Oh, here, Gabi is here. So we're happy to have you here, Aldo. To people who don't know, Aldo is everything. So he's a game theorist. Here is in the head. His head is a game theorist and cognitive science, I would say.
Yeah.
No?
Yeah.
Yeah, okay. And he's a game theorist, but an economist, mathematical economist, and microeconomist, and macroeconomist, and decision theorist, and neuroscience, neuroeconomics. And this is only part of what he's doing. And we'll hear about repeated prisoner's dilemma.
Yeah.
And IQ. So I'm making it shorter.
Yeah.
Please, Aldo. Thank you.
Thank you so much. I wish I was in Tel Aviv. I miss it. I haven't been there for a long time. Yeah. So the topic is this: strategic behavioral intelligence. And I thank immediately my co-authors because sometimes I don't get to the end, so I want to do it now. These are my two co-authors for most of the work I'm going to explain. Now, so this is, if you want, I can put it as in a polite conversation. This is a talk about two cities or two neighborhoods, but it could be controversial if you think about it as groups or countries. Let me explain. I mean, let me explain for spending one slide trying to explain what I'm trying to do here. The general idea is this one, that the wealth of nations and the institutions of nations are determined by the distribution in the population of basically 5 characteristics. One is intelligence, that's the one that we are focusing on today. The other one is conscientiousness, which is what the word suggests, how careful you are in executing the tasks that you are assigned to or you propose to yourself. Then the two next are the classical one, economics. The next 3, risk acceptance, patience, how much you value the future, and the trade-off between utility of income and this utility of work. Now, the emphasis is not only on the wealth of nations, but on the institutions. So I think that these 5 factors determine not only the wealth, but also the institutions that a country can afford. So in particular, when I will talk about intelligence here, I would focus not so much on this direction that intelligence is, the distribution of intelligence in a population is affecting what the country can do, because that's fairly obvious. I mean, having a better CPU is probably better, but also on the quality of the institutions that the country can afford. Okay, so the link that I'm interested in here in this study is the link between intelligence and institutions of a nation, and in particular, the level of cooperation that is sustainable within a country. Is that clear? So that's the main thesis. That's what I'm really after. And all of these characteristics are, in a substantial part, heritable. So that is a characteristic of nations that has a very large inertia over time. That's the general research program, okay? So just to explain that I'm going somewhere here. I'm not interested in, oh, look what a cute effect we find here. That's the general idea. I think it's fair to say. Okay, so let's look at what we do here. One is the first contribution here is how intelligence affects equilibrium selection in repeated games. So these papers are, the 2 papers are published. You can find them. One is now forthcoming. You can find them in my webpage. So here is the obvious part. In zero-sum games, the higher intelligence person wins, typically. So that's not the interesting part. The interesting part is non-zero-sum games when there is room for gains from cooperation. That's what I want to explore. Now, there is a view around that was introduced by my former mentor, rather in an old but influential paper, Can Bounding Rationality Resolve the Prisoner Dilemma? He was considering the one-shot prisoner dilemma. And the answer to the question was, of course, yes. And the intuition behind the paper was that agents might be too smart for their own good. So if you are too smart, you end up in the defect-effect equilibrium. If you introduce an epsilon of bounded rationality, you may sustain cooperation. That was the main idea. Main idea, you may be too smart for your own good. In the planet where I live, I have a different view. I think it's usually good for you to be smart.
Radner was a repeated game? Repeated game or
no. So Roy considered the one shot. That's here. I developed the opposite idea, but in repeated games. Okay? But I just want to, the setup is different. I just want to contrast two intuitions. Okay? Because in repeated game, this is where all the action is, because there is a surplus to be shared, and that's where intelligence, we will see, has a lot of leverage. So the setup, this is an experimental paper. It's just trying to make the point, develop the opposite idea. The setup is infinitely repeated games, symmetric games, 2 players to action. The stage game is 2 players to action. And we choose these 4 games, which are, if you think about it in the shape of the matrix, these are representative of the strategic situations that allow gains from cooperation. What this sentence is trying to say is that these 4 games are fairly representative of what you can have in symmetric 2 players to action games. So one is the Prisoner Dilemma, Battle of the Sexes, the Stag Hunt, and then a game that you will see that is a Battle of the Sexes with a compromise. It's basically the Oak Dove, but made non-generic. Okay, so that's the setup. The question is, how is intelligence affecting equilibrium selection in repeated games?
Small question.
Yeah.
This would be like the simple setup of a prisoner dilemma, not something like with the k-rationality. So it's like with a huge matrix that they fold up to the right. Like with you need to make a bet about like a number, and it turns out that it goes all the way down. You know what I mean?
Yeah. No. This is a simple
dilemma.
But it's. So I use the term here repeated, but it's really repeated games. You will see the details.
I understand, but I just wonder whether in a setup which is requires a little bit more of intelligence about how to solve it, backward induction, so to speak, whether the smartness can be a problem. Because I think we know that sometimes in these kinds of games, if you play it with lots of people, the equilibrium of the game, which is like really the best solution, is just if you think about it too much. Everybody, when they come up like betting on, like, with the game of 300, they bet like 295, doing like 2-3 backward induction and stuff. Okay.
Then I understand the question. Look, it's a fascinating topic, intelligence and games. I mean, there are many factors that one consider. For instance, the fact we are now looking at an example in which players know the level of intelligence of the other. Now, this introduces yet an additional difficulty, right? Because if you are playing with someone who is that that is less smart than you, then you might be tempted to take advantage of it. So there are many examples. The one that you suggest is another one. So let's say that we are starting to understand how things go. Okay,
Okay.
it's a limited setup. So the experimental design is create two cities. So two cities, I mean this. So here is two cities. One is in some neighborhood. This is called Belmont. If you don't know what I mean, and this is called Fishtown. If you don't know what I mean, it doesn't matter. But I mean, these are code words. This is the high IQ, and this is the high IQ. This is the low IQ. You see, I mean, this is of course a high income. This is a high income. You can see it from not just from the chimney or from the slated roof, but from this. Can you read what it is?
No, what does it say?
Can you read it now?
Oh, yes. Bleak manner. Yes. Okay.
So it's a sure sign that you are in an affluent neighborhood when you see a sign like that. If you know something about America, that's how things work.
White affluent neighborhood.
Excuse me? Affluent.
White affluent neighborhood.
Yes, that's the only kind. But it's an important, I mean, this is an important sign, right? It's manifesting a willingness to be cooperative up to a point. So we create these two cities. And the way in which we do it is experimental is this. We collect also one day and then the second day. It's usually 2 or 3 days apart. So in the first day, we bring them in, we collect information of who they are, what they do, what is your favorite color, their IQ, what is the name of the girlfriend. So we create a bit of a dust, but we also smuggle in an IQ test, which is not presented as an IQ test, but it's the classical Raven matrices. So we measure their intelligence, among other things. Then between day one and day two, we create a group of low intelligence and a group of high intelligence. And then we make them play within themselves. And they play repeated games repeatedly with random matching and a continuation probability. So after every period, you draw a coin, which is 75% head. And if it comes head, you continue. And if it comes tail, you stop to simulate the discounted. That's the standard way in which repeated games are implemented in experimental economics. That's it. So this is the treatment. So it looks like this. This is the distribution of IQ over all the sessions. And then when you split them, this is the high delta. So the delta is going to be what I said, the 75%, the continuation probability. It's a probability, but I call it delta to emphasize the link with repeated games. So you split them at the median, okay? So this is the low, and this is the high. This is the low.
Do the players know anything about the groups?
Excuse me?
Do the players know anything about the groups?
No, they only, no. I mean, so the emphasis is they don't know anything about the distribution of intelligence. They don't even, the word intelligence is never mentioned.
I see, okay.
So as I said, there is now an interesting experiment we are doing, which we tell them, you are playing with someone who is smarter than you. Go ahead, make your move.
How is it related to the cities you mentioned before?
Oh yeah, so this is the high intelligence city. This is the low intelligence.
I see. Okay. That's just a metaphor. Okay, good.
It's a fitting metaphor.
Yes, okay.
You observe the behavior here and here. I'm claiming what my little experiment tells you. It tells you something about the behavior in this city or in this city.
Okay.
So it claims to have some predictive power. So I'll focus here on this, the games for which there is room for cooperation, which is the prisoner dilemma and the battle of the sexes with the compromise. Let me explain. Battle of the sexes, if the battle of the sexes with the compromise is this. So first, prisoner dilemma is this one. has the characteristics that you know, but I want to emphasize, the difference between conditional on the cooperation of the other. The gain between to go to the effect is fairly small. Okay, these numbers have to be chosen accurately. If numbers are different, it may happen that nothing happens, of course. Every group, everybody goes one direction or the other. So this is, I'm just saying, these numbers are expensive numbers. You need to find them, because you need to find that point at which the effect is clear. The battle of the sexes with the compromise, so if there was a 0 here and here, it would be the classical battle of the sexes. But here we put a possibility of a compromise, so we choose a combination that is not optimum, but fairly good for both of us. Otherwise, we can insist in deviating to these two most preferred outcome, one for player 1 and one for player 2. And of course, 48 is larger than 52 plus 12 divided by 2, so it's really better to concentrate on this. So the green one is what you should do by cooperating, and the red one is what you get in defect, and the corresponding of defect in the battle of the sexes with the compromise is trying to fixate in one of these two outcomes, which are Nash equilibrium of the one shot and also Nash equilibrium outcome of the repeated game. Okay,
what are the real payoffs of the players?
It's about, I don't know, 12 overall at the end of the game is in the order of 30 euros, 25 to 30 euros. Is that okay?
Okay.
So, well, you will see there is an effect on pay.
I see. Okay.
Okay, so first we look at the prisoner dilemma with the high continuation probability. And now you will see two graphs that present the cooperation level. What I will focus on is the cooperation level in the high IQ and in the low IQ.
What is the sense in which 75% is high?
Higher than 20.
Okay, it's higher. So one is 75% and the other one is 50%.
But with 50%,
so high
probably
means higher than 50%. Again,
No,
all these numbers.
I understand, but with 50%, the game ends fairly rapidly, like after a few. Yeah.
Yes, but all these numbers are relative, right? I mean, it's you are making, as I mentioned at the beginning, you have to find the right numbers.
Okay.
Of course, you can compute. You can take these numbers as utils, take them seriously, and compute and see what equilibria are sustainable or not.
My impression was that in repeated games in the lab, they use higher numbers than 75%.
Yeah. So again, I can, if that is what you don't like, then I can change.
No, it's not a matter of liking. I just wanted to understand what you did.
It's fine. I mean, the problem with 90% is that then you have to put a termination rule, because there are sometimes some draws in which you keep playing and then you have to stop it.
Right.
So the violation of your own announcement that wants to reproduce a stationary game becomes really strong. You see, that's my objection to the 90%.
Okay.
You can put 99 if you like, but then you have to,
sure.
It's getting late, let's stop here. So that's the trade-off I have in mind when I design experiments.
Okay.
Okay, so here is the main, if you had, wait a minute,
By the way,
conjectures?
Do the players know the probability of ending the game?
Yes. Everything that I explained to you is known to them, except the characteristic of the population in the game. So I don't know if you have conjecture, but here it is. This is the high IQ, and this is the low IQ. law.
So what is this cooperation rate?
Cooperation rate is the fraction of the time, or we take average. So here is time. Time, I mean, during the experimental session.
Yeah.
Okay. And then you can take windows and you can compute. So this is one window, this is another window. I can compute the average cooperation rate. So the average fraction of the time in which you play this.
Yeah, okay, but there are also a lot of times where only one cooperate. You don't count them.
Yeah, yes, that's the fraction of the time in which both cooperate.
Yes.
That's a very summary statistics to give you the idea. They start more or less at the same level. This one goes approximately to 100%. This one sticks to around 40 to 50%. So that's the first period cooperation is the same in the two groups. The first period payoff, if you look at the statistics here, is very different. Note that the time for the law is the number of games played for the law is smaller than the number of games played by the high, because these players also decide faster. We left them deciding how much time they needed. So high IQ not only are more effective in reaching a cooperation rate, but they stay on the cooperation phase longer.
By the way, it's only IQ, or are there other characteristics that are highly correlated with IQ, and therefore the results are driven by something else?
So that took 2 years of additional experiments. I'll touch on it. That's a very good question.
Sure.
Is it possible that the people with the high IQ here, coming from the richer neighborhoods, have a knowledge about this game more than people from the poor neighborhood? So it's not about playing the game, but already knowing what to do?
Yeah, so
they don't start like this, but
yeah. So we acted on that possible objection in 2 ways. At the design moment, to try to eliminate all these factors. For instance, excluding all economic students or all the students that said they had even exposure to game theory, and trying to get them there more or less on a homogeneous group, because they are all going to the same public university. This is university in England, and so that's the first level in which we try to address that.
By the way, it seems to me that you could exploit this feature in a different way. You could imagine that if you test students at universities and there is some correlation between IQ and different departments, yes?
Yeah, there is.
So if they tried, I'm sure that they tried in the past on different departments, students from different places, to check for this feature, you might find this, so I don't want to say the departments now, but you could imagine.
Yeah, no, I completely agree. I think there is someone who finds this. The problem is that we want to stay away from, you're looking at mathematics department, so they compute the equilibria in their head. So we want to avoid that. We really try to go to the IQ part.
I guess you didn't use the term prisoner's dilemma.
Well, no, of course not.
Okay, good.
No. My goodness, that is a no. No.
I have a question regarding the game here. So you said that the game is played 30 to 40 times. So in each instance, they play a repeated game with termination probability of 75%.
Yep. So the game is the session goes on like this. The people come in. We make a random match within the population. We create a pair. That pair plays a repeated game until termination. We random match again, avoiding that pair. They know this. and then the new player plays again a repeated game, and then again and then again until the session ends.
And the games played is the number of the repeated games.
Yes.
Right? Not within the games. Yeah.
Yeah. So
Thank you.
that's really the main finding. Something similar happens in the battle of the sexes with the compromise. The high IQ focus more on the compromise. The lower IQ are not able to do it. They shift to 52-12 or 12-52 outcome. And again, the payoffs are lower for the low IQ and higher for the high IQ. Okay.
And
So
Aldo, how many participants were participating in the experiment?
A lot. I forgot the numbers because this is a while ago. It's a lot. I mean, I don't know, several hundred. At the end, this was a monster experiment because people didn't like this. You will see what the objections are. I will make several points that are all points that the referees raised. So the first one. So why this difference? So okay. So this is just a factual observation. By the way, it's robust. Now we have replicated many times. This always happens. This always happens.
Just a moment. You said that if you change the payoffs, for example, so you
No. Okay, this always happens in the sense if there is a difference in behavior between the two groups, it always goes in the direction of the higher IQ cooperating more in a game like Prisoner Dilemma or Battle of the Sexes.
So for
what may happen if you choose the numbers wrong, for instance, here is an example of choosing the number wrong. I mean, that is what may happen. If you put with the same stage game, but you lower the continuation probability to 50% instead of 75%.
You don't.
I don't know if I don't have the slides. You will see that. So this is an important test because so here is an example of what I was saying, right? In this point, the equilibrium at this level, the behavior of the two groups is very similar. In fact, if you see the higher intelligence are the first one who defect. So to speak, they realize that the continuation value doesn't matter, so there is no point in cooperating. So this observation that the behavior of the two groups is similar when the continuation value is 50% instead of 75% supports this claim. Someone might say, there is a natural tendency of higher intelligence people to cooperate unconditionally. That's not true. Is that clear?
So they're not intrinsically more cooperative than what are they? So it's more rational to play cooperative in a repeated, in a long repeated game.
Well, don't tell me I have only 10 minutes. Okay.
I still.
I'm trying to get to the answer to the question: what is the reason for this difference? If you want, I can spoil the suspense and tell you what
No, don't.
No, the other possibility is, intelligence is one of the many things that matter. There is conscientiousness, there is agreeableness, there are many other, there are big 5 personality traits. You can consider them all. Of course, there is one natural candidate, which people that like social preferences support, is that what matters is really how much you care about the other. Which is the facet of altruism in the big 5, which is as a sub-trait of agreeableness. Okay, sorry, technical term for personality psychology, but there is something in personality psychology which is called agreeableness, which is the closest thing to social preferences in psychology. So we ran this experiment, exactly the same design, but splitting the group, not in high and low IQ group, but high and low agreeableness, for instance, high and low conscientiousness, trying to see whether this would make a difference. So the main thing is that agreeableness has a very small effect compared to the effect of IQ, and the small effect vanishes after the initial games. Other traits have no effect. So this bullet point is saying there is something specific about intelligence, and it's not that they are unconditionally cooperative. So, okay.
Mm-hmm.
So the main answer, I have to start accelerating here. The main difference here is if you start looking at what they do, and in particular what they do when the partner cooperated in the previous time, whether they answer with a cooperation or not, you will see that there is a subtle difference in the fraction of players that respond with cooperation. This is the red, remember, is always the low IQ, and the blue is the high IQ. So they respond more to cooperation of the partner cooperation. And so the main difference happens here when in the retaliation phase. So whether they play cooperation against the defection of the other partner, of course, the average number is very low, is about 10%. But there is no substantial difference between the two groups. So the big difference is here. So the same thing happens in the battle of the sexes with the compromise. Mm-hmm. So the main hypothesis that we formulated here, and then we tested it in the next experiment, is with a more theoretical structure, is that even if players with lower intelligence are able to understand that there is a strategy that consists of cooperating and sticking to it, they tend to fail more frequently, do something that we can call for convenience and error. They err more often with respect to the strategy, and the overall outcome is that the cooperation unravels and they end up in this situation. So it's really a story about error rate with respect to the strategy. There's also another aspect, which I know I will not have the time to examine, is that higher intelligence people are probably even better at conceiving a larger strategy space. So I won't have time to go into this, but for those of you who know forward induction, higher intelligence people are those who understand forward induction, and lower intelligence people don't understand. So if you think of forward induction as yet another behavior that is available to you, higher intelligence people can conceive it, lower intelligence people do not. Let me go quickly to the next topic here. Moving to opportunity. I'm making fun of it. Moving to, you know what moving to opportunities, right? You take the lower, the poor city, and you move it to the high city, hoping that there is a beneficial influence. What happens if you put the high intelligence and low intelligence people together? So the bottom line is this. Higher intelligence individuals teach cooperation with punishment. So you will see that, let me show you the results. So that's the next paper. Moving to opportunity. In this, we use a design which is very similar to that, but we compare the behavior to that we have seen. Well, we compare the behavior in split groups, which is the experiment that you have seen, intelligent and on one side and less intelligence on the other side, and we pooled groups. We put them together, and we see. So this would be the move into opportunity. We put the lower intelligence together with higher intelligence and see what happens. What happens is this. So lower intelligence learn to cooperate because this is what happens. So this is the fraction of cooperation again between the high IQ, which is this, and the low IQ, which is this. Again, over time, in this, when they are taken separate. So this result, as you see, replicates the one that that we had at the beginning. When we put them together, the cooperation rate is this, which is very similar for the two groups and is approximate intermediate between the two. And the payoffs are similar. So lower intelligence people learn to cooperate, but the cooperation rate is at an intermediate level between, so it's sort of the average that you have between the average of the cooperation rates that you have in the separate groups. If you do the analysis of the data, this, I don't know, all the analysis is done in the paper, is very careful. You see that lower intelligence players learn to cooperate through tough love, in the sense, tough love of the higher intelligence people is the higher intelligence people are much stricter in enforcing the punishment. In fact, you will see that they are stricter even in enforcing the punishment on the higher IQ players. So what happens then is that in pool groups, there is a general phenomenon in which lenient strategies are reduced, the fraction of lenient strategies. So for instance, the fraction of always defect increases and the tit for tat and grim trigger decreases. So what is driving this result is the following fact. Higher intelligence people, as soon as they deviate, they switch to harsher strategies, and they are much harder to come back away from the harsher strategies. Okay, so I realize I'm getting out of time. I want to announce you that we think this is a general phenomenon, and I want to explain in what sense this is a general phenomenon. So I'll just make the claim, and then you tell me how we proceed. The general phenomenon is this. This repeats what I said before. In mixed societies, so when the fraction of lower intelligence is higher, you see harsher strategies emerge in our game. If you make an evolutionary model of this, you get something like this theorem. Societies with lower intelligence, so that we identify in our model, because we can estimate. So this we can measure, this we can estimate, because we can reconstruct, we can model strategies as automata, and we can see how many times within this model a player commits error. There are, of course, two types of error, but let's simplify here with the higher error rate. So in societies with lower intelligence, that is higher error rate, have harsher strategies more frequently. I'm claiming this is a theorem. It's a theorem. I mean, it's a theorem. Okay, you derive it from analysis of evolutionary behavior in repeated games.
Harsher,
so I would pause here. Harsher.
You mean that they are less forgiving, the faction?
Yeah, yes. So there is a subtle definitional issue here. It's almost like less forgiving. But in the set of strategies that we are considering, in the analysis that we do, always defect, grim trigger, and tit for tat. Always defect is harsher than grim trigger, which is harsher than tit for tat.
In your evolutionary analysis, you had these three strategies in the population, or you measured only two at a time?
So from now on, one can make a model and then try to bring it to the data. Since we want to bring it to the data, in repeated games, Prisoner Dilemma, the only strategies you observe are this.
But you don't really see that people play exactly these strategies, or do you?
No, but we have clever algorithms that can effectively, you can discuss how effective it is. But if you see someone starting with the defect, it's unlikely that is using this. Of course, it may be using this and do an error.
Yes. Mm-hmm.
So the parameter that we are estimating here is you do a maximum likelihood analysis, and we introduce the error rate, which we conjecture being related to higher intelligence. And in fact, it is. And then ex post, we do find that that it is correlated with intelligence. So I've spoken now for 40 minutes. Do you want me to explain what I do here, or
you can go for a few minutes more, okay? Because we interrupted a lot. Okay.
Okay. Okay. So I'll explain the spirit of here. So remember that we are playing repeated games, in the sense that players that the model matches exactly the experimental setup that we had. So players in a population are randomly matched. Each pair plays a repeated game. So it goes on for 5, 10, depending on the tosses of the coin. And then at the end of the repeated game, there is a new matching, and then a new repeated game is played. Okay, so that's the model. So it's a repeated game. And so we can model this by thinking that in every repeated game, a player chooses a repeated game strategy. For instance, chooses always defect. And he has some idea, if you want to make it a purely Bayesian model, has some idea of the distribution of the strategy in the population. So maybe he chooses always defect as the best response to his belief. And then he has this matrix of payoff. This is the matrix of payoff you get from the stage game, given this discount, if you are matched with a player that is using the other repeated game strategy. For instance, if you match 2 always defect, of course, they always get the defect payoff. If you match an always defect with a grim trigger, the always defect gets a traitor payoff in the first, and then it gets always defect, and so on.
By the way, how many times the game is repeated? The repeated game is repeated? How many repeated?
It's about, in the data, it's about 15 to 20 times. So the key observation here is that there is a big indeterminacy here, because it doesn't matter if you are the grim trigger and tit for tat give the same payoff in this choice of strategy repeated game. What is crucial to observe here is that if I introduce a small error, okay, sorry, I have to say what is an error. We model strategies as automata, so I may assume that an automata is just a set of internal states, a choice function that associates an action to an internal state, a transition function, and then an initial state. And players can make 2 types of error. One is an error in transition, so in applying the transition function, and then an error in action choice when we make an error implementing the choice function. We can somewhat distinguish between the 2 types of error. The crucial thing is that if you introduce this error, so if you allow strategies to be implemented with some error, the payoff matrix, this of course changes, but now this indeterminacy is broken, because an error when you are playing game trigger is more costly, right? Because there is no way to recover. You need another error to get out of the defection. So you will see that these numbers fall faster than this number if you do the analysis. That's the basic intuition. So indeterminacy is broken. Is it clear what I'm saying? Mm-hmm. Here, that you cannot say where the frequency of strategy goes, because there is no difference. As soon as you introduce error, you see the indeterminacy broken, and you see an interesting pattern arising.
You introduce the errors by assuming that with some probability they they make the wrong choice?
Yes, either they make the wrong choice or they transit to the wrong state.
Right. Yes.
Okay, and again, we can the error frequency that we use in the model are the error frequency that we estimate in the data. The error frequency is small. It never goes to, so it's around 3% for high intelligence. It goes to, at the beginning, it goes to high of 20% for the low intelligence at the beginning. So I call this small error rate. I don't know, maybe a big for you. I mean, that's the order of magnitude.
So low intelligence people make more mistakes?
Yeah. Yeah. Okay. Yeah. So we use best response dynamic, and then you can do the analysis on this on the three strategies, and you will see what happens in the basin of attraction of the three strategies. So I put here basin of attraction. I mean, this I have this, since there are three strategies, the simplest I project it to the tit for tat and green trigger space, and I see the basin of attraction of the three strategies. So for instance, if we converge here, it means that everybody's playing always defect. If it converges here, it means that everybody's playing game trigger. If it converges here, it means that everybody's playing tit for tat, okay? So that's the basin of attraction of the three. What happens at epsilon equal to 0? Epsilon is the error rate. Epsilon equal to 0 indeterminacy. It really matters how you break the tie in the best response dynamic. As soon as you put a very small error, look, there is a huge difference between this, and this is tit for tat, and this is green trigger, and this is always defect. Small error, very large basin of attraction for tit for tat, for the least harsh of the three. And then as you increase, so now you will see different pictures. This is the computation of the equilibrium. This is not Monte Carlo, just looking at what happens at the basin of attraction. If you increase this epsilon, you will see that this region will become smaller, and the region, so remember, this is tit for tat, this is green trigger, and this is always defect. So this becomes bigger, and this becomes bigger. So green trigger gains from tit for tat, and they both lose to always defect. Okay, I mean, that's the mathematics of it. Mathematics. I mean, that's the analysis you get. That's how what you get with the 25% error rate. So this matches very well our data. We think it's an explanation of what we have observed if we focus on error rate.
So again, how does it explain the results that you got?
Yeah, so the result is, the intuition is how, let me go back. This is the matrix of payoffs in the choice of strategy in the repeated game. This is when error is 0. When you put error larger than 0, epsilon is error. These numbers change. These numbers here change, and change to the advantage of always defect. That's the intuition, but and it's really obvious when.
So you're saying that less intelligent people tend to play more always defect?
Yeah.
In a society with less intelligent people, we are most likely to observe always defect strategy. In a society,
the more intelligent.
This is a society of high intelligent people. This is a society of low intelligence people. It fits the pattern I observe casually, and it fits the experimental data.
So the more intelligent people tend to play tit for tat more often.
Yeah. Well, they tend to be more
I think you need to think,
because they can afford. Because you see, because they can afford it.
Yes, but
I mean, I
previously you
can
said-
really interpret an error. Is not, you're not right. I mean, it's well, you're smart. You're not going to do it again. So I can afford it. That's the intuition.
But previously you said that the more intelligent people are less forgiving, which is inconsistent.
Yeah, no, they're less forgiving. Yeah, they're less forgiving than they are when they play within themselves. Take a very high intelligence city. Start putting lower intelligence. You will see the high intelligence become less lenient.
So I thought that you said that less intelligent people tend more to err. I thought that's the explanation.
Yes, yes. So the fraction of that's what I'm trying to capture by saying.
It's not that they are more lenient or less lenient. It's just about errors.
Yes,
to err.
that's is. If I take an evolutionary point of view, and I consider what happens in no, this is a purely evolutionary game.
Yeah, okay.
What happens to the frequency of strategy if one looks at the relative profitability of the different strategies? The profitability of harsher strategies becomes larger in a society in which the error rate is high.
Yeah, okay. So it doesn't stand in contrast to what Roy Radner observed or conjectured. I guess he didn't. For him, it was not an experiment. It was a theoretical paper, right?
Would you? I'm not sure. I think his bottom line was. Do you think this? I captured the insight of Roy as really, don't be too smart. It might be bad for you.
Yeah, but there, of course, you cannot reduce it to to a problem, a one-shot game to error of any kind. I mean, the basic idea here. Yeah.
Yeah.
There is.
I don't know. It looks like in this, if you look at the payoffs, you would really like to live in a higher intelligence society. In these games. Let's not stretch the comparison too much. Roy seemed to me to suggest you want to live in a society in which people don't really try to extract every single penny, because if they do that, they are, I know, he's a moralistic person. And you are too, I don't know, too intelligent or too greedy, and then it's not good for you.
Aldo, you might imagine that in a different setting, higher error rates might be good. I mean, if you imagine that when you don't make any errors, you are doomed to an inefficient equilibrium, yes? So error rates might take you out of it, right?
That's
so
right.
If you associate error rates with intelligence, it means that the intelligent people will be stuck with the inefficient equilibrium and will not be able to get out of it, while less intelligent people will by chance make this error and will get out of it. I think there might be this kind of situation that the question is whether the setup that you have in mind is calling for a situation when they are eventually at the good equilibrium is you understand what I mean?
I understand perfectly. It's the trade-off between exploration and exploitation. I agree. I understand theoretically the point you are making. I appeal to the economist. You think this is a first-order consideration? I mean, what is ruling here? If you take this point of view, I want to explain wealth of nations and the institutions that they can afford. I mean, there are many ways in which you can explore. No? In the States, but I
can share for
theoretically, I agree. Experimentally or empirically, it's a fascinating question. My bet is that the exploration part.
No, but Elon, can I share just for a second the screen?
Excuse me? You want to share the screen?
I'm asking for Elon for this permission.
Elon, yeah, it's fine for me.
Just 1 second, so I'll stop you, I think. Do you see this one?
Yeah.
I mean, this is what I talked before. So it's the traveler's dilemma that
I see.
comes down
Okay.
to the prisoner dilemma in a 2x2 setting, right?
Uh-huh.
So like if you start from the beginning, it's like you need to make how much you are claiming for something, right?
Uh-huh.
And there is this experiment here about what people are doing, right?
Uh-huh.
And it seems that the smarter you are, you will tend to the inefficient equilibrium of stating the lowest amount. And if you do a spontaneous claim against another, maybe both of you will get everything and you cooperate very easily. So,
Yep.
so I wonder whether in this kind of situation, if people like the smarter are would be doomed to. So it will not be a repeated game. It will be a one-shot game. The longer you play this one-shot game with other people, you will start to understand the mechanism. And if you, so
it's clear. Wait a minute. It's clear. I understand. I understand. So, did you try to do the
No, I'm not doing the
intelligent part?
No, I did not.
Okay, can you send me those slides? Those are public slides, I assume.
Yeah, sure. I'll send it to you. It's
because then I can think more.
All right. Okay.
Seriously about it.
So I wonder. I remember many years ago, I talked to somebody. I'm not sure he published it. He gave chess players. He asked them to play the Centipede Game.
Uh-huh.
And his conclusion was that the higher your rank in chess, the faster you'll converge to the equilibrium, which means you stop the game immediately.
Yeah.
So this is a game where it seems that intelligence is detrimental. It's not good to be intelligent. If you're not, then you don't understand what's going on. You'll continue for some time.
Yeah.
So
I agree. I mean, in the spirit of say competitive games, the other rule appears that but I mean,
what is competitive games?
No, I mean, I'm just saying any game in which your payoff is increases if the other player decreases. It depends on what form of the centipede you are using.
Oh, yeah, the usual centipede, they both increase only momentarily. If you go ahead, then of course it increases dramatically. But just the next step is not very nice.
Okay.
Roy has a question here, so maybe you can ask him on behalf.
So Aldo, Roy doesn't have a mic, so he asked in the chat, for effective institutions, you need some stability, and the people who score low on the Raven are less stable. But this is implicit institutions. If you let them send verbal messages, it might substitute for intelligence. Have you tried that?
Yeah, so what is might substitute for intelligence? I didn't understand what.
Okay, so maybe Roy will.
I understand. So if they send messages, that can play the role of intelligence. Yeah. No, we haven't tried that. The closest thing we have tried is this: is that players can be informed of the level of intelligence of the other. There we see that there is some tendency of the higher intelligence to take advantage of the lower intelligence. So that may be detrimental. But if the question is, have you tried that? The answer is no. If I think that it will affect the outcome, my guess is that the higher intelligent people will be more clever in interpreting the verbal messages that they send.
I try to.
That's okay. So now you're in with the microphone.
Yeah, I switched.
I was trying to guess. If you want to do it, I'm happy to do it. We can see what happens.
Yeah. So right.
So free flow, right? Free flow.
Yeah, that's free flow. Yes.
Yeah. So my guess is that they are more
Okay.
clever in.
Yeah, it's related, I think, to Avram's question about the traveler's dilemma. I think your point is about institutions, which you only get in the repeated, right? The institution is we need to cooperate in the repeated game, and that's how you get the benefits of cooperation.
Yeah.
It shouldn't work in the one shot, like it doesn't work in your data in one shot or in the first round in prisoner's dilemma. There's no reason it should work in traveler's dilemma because it's all about setting the rules on how we cooperate over time. And that's why I'm saying if we can explicitly set the rules and we discuss it and we say we do tit for tat or something like that, then you might diminish or extinguish the difference based on the Raven.
So that's
people
I think
need
maybe,
to figure out that the other
now,
guy is using
you are making a very complex game of bargaining, right? I mean, because maybe this guy is trying to convince me. It's in this sense is a little bit related to I tell you that I'm more intelligent than you, because maybe now he's trying to take advantage of me. So I don't know. My bet is still on higher intelligence being more effective, but. One has to try this. It's a completely different dynamic than the simpler one that I'm trying to identify, which is really a story about understanding what are the strategies available and how good you are at implementing them.
But there's a lot of coordination here, right, in the repeated game. That's what the institution is.
In the one shot, I almost know the answer because I know that already with 50% continuation probability, which is still far from the one shot, but it's closer. Higher intelligence people defect faster than lower intelligence.
Yeah. So we cannot choose to be more intelligent, right? That's not a choice matter.
I have a question.
Yeah.
I mean, I'm not sure if it's relevant, but I'll try. I mean, this is a prisoner dilemma setting, right? Suppose you were trying, and I wasn't sure about your battle of the sexes with the compromise, but suppose you were trying like this hog-dove game with the two equilibrium, and you need to make a selection between the more efficient equilibrium and the risk-dominant equilibrium, for example. I mean,
so the battle of the sexes is close enough to that. The only difference is that the dove has a tie and we don't want that tie. But I think that's the flavor. There is an equilibrium which is efficient, which was the 48-48, in which they both get enough value, or they try to go to the other two extremes. So that's really the flavor of the oak-dove game. And the higher intelligence seems to understand earlier on in the game and keep that the efficient equilibrium. So I'm just saying that in the.
But basically the idea would be that if you put into so if you introduce to a hog-dove game, evolutionary game of a hog-dove with error rate, so the higher the error rate, the basis of attraction of the inefficient equilibrium is getting larger, and the smaller the error rate, the vice versa, right? That would be the point.
Yeah, if it extends, I don't know. The analysis I did was only for the prisoner dilemma.
Okay.
The intuition is tricky here because these matrices change, so you have to be careful in estimating how the error affects the payoffs.
But there is an intuition here, right? Because if the error is really large, it's like a one-shot game, and you know what happens in the one-shot game.
No, but with the prisoner dilemma, you know what happens, but in the
but in general, you can get cooperation by reacting to what your partner did in the previous rounds, right? That's how you get cooperation. And if you have lots of error, then you cannot react to what they do.
Or it's not convenient. Yeah, it's not convenient.
In the hog-dove game that I have in mind, it's not about cooperation. because the two equilibrium, different people are gaining. So it's not that that there is one equilibrium which is better for the two players than the other one, right? So it's like there is one equilibrium that one player gets a higher payoff than the other. The other equilibrium, it's the reverse of it, right? And it might be that if it's not symmetrical, that one is actually better in some sense overall. But it's not that they want to cooperate necessarily on one. They don't. They have opposite preferences.
That sounds like a battle of the sexes, right?
No, it's chicken. It's more like chicken.
It's chicken. The
Well-
origin of the chicken, yes.
Well,
It
in
is,
the
but
battle of the sexes, with the compromise, there is the race is between one strategy, which is to alternate between the two, the ballet,
Yeah.
or in the compromise. It's hard to see what happens in that situation.
Okay. Very interesting.
But if I summarize your point, the main point is if you think about intelligence as an error rate,
Yeah.
check for whatever equilibrium in a dynamic setting, how the error rate affects the outcome, and do the association between intelligence and the result. That would be the 3 steps that I think of.
As a general recipes, and you take the size of the basin of attraction as a reasonable measure of what you can expect to be the frequency of a strategy in a real game.
Yes.
So that you can do the analysis for any game. I mean, it's an interesting exercise. I haven't done it yet.
And why did you use, I mean, apart from trying to make it richer, why did you need to use the 2 measures of the error about the transition and about the error in applying the strategies?
Well, we are forced to do that in the analysis of the data because, first of all, I mean, it's a nice, I think it's a nice distinction from the theoretical point of view, because the error in action is really, I mean, in the general project that tries to identify what personality characteristics are important, I can identify an error in action more with how cautious, how conscientious you are in your choice of actions. And the error in transition is much closer to the understanding the strategy. Really, if in the transition, what comes in is the working memory. You have to remember, I am in this state, I observe this action, I have to move to this next internal state. So I associate error in transition with failure of working memory, error in action with failure in being careful in your choice. So I think it's an interesting distinction. Then when you do the analysis of the data, you realize that the 2 things have very different effects, because if it is an error in transition, that means that the state has changed. So that if you are playing with a green trigger and it's shifted, then that might be more permanent. Here it becomes very subtle in what green trigger strategy, what is the automaton that you're using to model the green trigger, because it begins to depend whether you shift to defection, depending on whether only the other defected or whether either of you defected. So it gets into more subtle issues. I don't know if this is clear. I mean, green trigger becomes, when you model it as an automaton, has 2 different models. I'm just saying this. And the interpretation of the difference between transition, error in transition and error in action is different in the 2 interpretations.
Okay.
So
Maybe this is mysterious.
What is the epsilon in your work? Which one of the 2 errors? Or the both? Did you assign both the same probability, the same epsilon?
No, I try to in the So in the simulations, in the numerical computation you saw, I was only looking at the error in transition.
Ah, I see. Okay.
If you look at error in action and transition, then you can do a more complicated diagram depending on which one it is. I was just warning that this difference becomes relevant in the prisoner dilemma only when you take a different interpretation of green trigger.
I see. Okay, good. Mhm.
One last one. If you just, instead of doing 3 strategies in the evolution stage, if you play just 2, for example, what would you get? Would it be better in any way? Like if
Yeah,
they
it's the
take
same. It's the same. You see, you get what you get in the projection of the simplex on the sides.
Yeah.
So you can see what happens in the side. That's in fact how you do the analysis.
Okay.
You can see at the breakpoint on the sides of the triangle,
Okay.
and they move in a very regular way. That's how you understand what is going on.
In the 2 cases.
And the pattern is the same. So if you look at only green trigger and tit for tat, you see that it moves the split of the segment goes in favor of green trigger as the error rate increases.
Okay.
If you look at the side, green trigger and always defect moves in the direction of always defect, and so on. That's how you trace it back to the effect, to the projection on the sides of the triangle.
Mhm.
So there is very clear what is going on.
Okay.
Mhm.
So what do you think of the general program? Any comment on the general program?
I think it can be generalized.
Good.
No,
I'll work on it starting today.
I've done a paper about this this chicken game with role players in like a low economic setting with drivers and pedestrians with an evolutionary game. But it would be interesting to introduce to this something like a stochastic random error. To see whether like how different things affect the basin of attraction of the different things.
Yeah, it has a lot of introduces a lot of interesting stuff.
I'll send you something and
okay,
we'll see maybe.
Okay, I'll be happy to.
Okay, thank you very much, Aldo.
Thank you, Dov. Thank you, everybody. Thank you, Alan, for inviting me.
Thank you very much.
And
okay, stay safe. Well, you don't need to stay safe. I'll try to stay safe.
Yeah.
Okay.
So that's a question of institutions. This is a question of institutions.